Hello everybody. I'm filming at home right now, so may look a little obviously different from our glass room. This is actually my staircase where I live. Anyhow, we're on schedule to do section 7.1 today. And so if you want, since we would in theory be starting to build toward test number 3, if you are so inclined, you could fold over maybe a piece of loose leaf and designate this chapter 7. Basically, we're going to cover something called unit circles, and in keeping with the sequence of more and more functions, we're going to be talking about the trig function, sine and cosine function eventually. Anyhow, there's a lot of handouts I would have given you today. I'm going to sort of point to them as they come up in the course of conversation. And when I post the video, I'll try to put everything in announcements so you don't have to go digging for it. Anyhow, here's an overview of what section 7.1 would be. This. Basically, there's a lot of terminology that we have to discuss. So I'll try to elaborate on certain key phrases that are good to know and sort of construct a table. And then there's measurements. When it comes to terminology, I want to give you a copy, basically, of the Greek alphabet. This is one of the handouts, again, I would have given you in person. The Greek alphabet, those letters basically get used a lot in math and in science. So when I refer to a Greek letter, it will be a peculiar looking thing if you've never seen it before. It's actually where the Roman alphabet is derived from. Let's see. Of measurements, there'll be basically conversions, let's see, that are good to know. Basically, they're a formula converting from, say, degrees, which you've probably heard of, to something called pi radians, which you may not have heard of. Right. And pi radians itself can be converted to just ordinary radians. Another unit, if you will. Technically, pi radians are unitless, but if you assign a word to it, technically is a unit then. Not to confuse you. You'll see what I mean when we get to that point. There's also a list of special angles that are good to know. This is another handout. And some formulas. Okay. All right. Let's start with some terminology. Okay. There is a sheet I had probably. Trying to think if I had given your class this diagram before. If I hadn't, all right, it looks something like this, and there'll be a blank copy of this when I upload the video to Canvas. Right? It's basically a way of organizing some key phrases and what the related symbols would look like, or what abbreviations they would be. So let me try to duplicate this. I don't have a projector, unfortunately, so I'll sort of kind of finagle something here for you. All right. have our concept or the key phrase, and we have the symbol or abbreviation that might correlate to, and then a description to clarify. Since we're talking about angles, we have to talk about basic geometry. Some of this is self-explanatory, but better to start from scratch. Yeah. All right, we have the concept of a point, right? A mathematical point. Right? If you had a coordinate plane, a point would be represented by some dot, which is representative itself of a location. All right? It's what you would refer to as an axiom. An axiom is something that does not require a more fundamental description or more fundamental concepts to describe the thing. It is what it is. However, the concepts that follow are based upon that axiom. It is, for all intents and purposes, a dot in space. I have a diagram here I'm going to use later. I drew a coordinate plane. Okay. Next thing is, let's see, a mathematical line, which is usually drawn obviously like a bunch of dots, right, in sequence, headed off in some direction perhaps. If it's a segment, it usually ends at 2 points, and they'll label the points some letter like A and B. Or if it's a line that goes into infinity, right, they might refer to some points that are on the line. And the abbreviation would be something like this. Right? If it's a segment, it would just be like that, AB, referring to whatever 2 points you have that are on the same line. The key thing to remember from this is that a line is made of points. Right? It is continuous, which means there are no gaps. And maybe why that is makes it less obvious that it is in fact made of all of these points, because they're all connected. There is one immediately after the other. Okay, and you would refer to this in general as being one-dimensional. Whereas in theory, a dot is dimensionless. Moving on. Okay. The next thing would be a plane. See if my green works. There we go. What is a plane but basically a bunch of lines running parallel in one direction and maybe parallel in another direction until you get a grid. In the same way that a line is comprised or composed of points, a plane is composed of lines. And in theory, you know, if you extend it backward, it's a bunch of dots as well. Anyhow, this is officially something that you would refer to as two-dimensional. And it's usually to start out with horizontal dimension and a vertical dimension. We would refer to it as mathematically flat. What do I mean by that? Well, here's a very large piece of paper, for example. Right? It's a real object. right? Anything that is real is not really mathematically flat, right? If anyone has ever gotten a paper cut, they know that there is in fact a thickness to this. Happens to be very thin, which is why you get hurt if you rub your finger too much, right? But even a piece of paper, which colloquially, vernacular English, we in ordinary speak, we say, oh, this is flat, right? Yeah, in ordinary life we would say that, but it's not mathematically flat. For something to be mathematically flat, there would technically be no edge, no third dimension, no thickness, and no hazard of getting a paper cut, which I have actually. Just recently. Now, because I'm a little worried about the frame, my camera seems to end basically about here. I'm gonna have to erase a lot because I don't have a lot of real estate to write on. So what I'll do is, maybe I'll just turn this over. Let's see. I made this out of some plywood and a piece of acrylic plastic, which I just happen to have from old projects. So this is unfortunately cracked here, you can see. I felt so bad to throw it away, so I just kept it. Anyhow, hopefully it's not too noticeable. But I'll save that, and if I have to rotate it again. These points, these terms, which I'm going to write now, I'll specifically put in the same color. Okay. Most relevant to us right now is what is referred to as a ray. Ray in a drawing at least looks something like this. I'm not really happy with blue. Looks like an arrow with one point where it starts, maybe second point here. Let's just call this A and B again. Not being too creative. The point where it starts is referred to as an end point. And if you were going to abbreviate this in text, it would be symbolized like so. An arrow drawn above capital A, capital B. 2 points that happen to be part of this line somehow. But it is more accurately referred to as a ray because it is an arrow headed in one direction. It has one fixed point. And let's see. It will later be used to form an angle in relation to what we need in this chapter. Okay. If you have, let's see, I'm already defining myself. I want this to be clearly visible. A vertex is basically the location where two rays are united, joined. So if I'm just going to call this C, we'll call this point D and this E, the actual corner is the vertex. The corner of an angle. And bear in mind, there's a ray stretching this way, and there's a second ray stretching this way. You might say the point where rays meet. The common point. All right, we'll just simply call it the corner of an angle. Now as for an actual angle itself, an angle, if I took the same picture use the same letters, C, D, and E. The angle would be the measurement that would be between the rays. And there's two ways that you could abbreviate that at least. Let's see. If you're going to use this abbreviation, we'll see this small sort of angle symbol in text. Just beware, if you use the 3 points that are mentioned in the drawing, the actual vertex should be the middle letter. Right? Alternatively, what they'll do is they'll have some letter written inside this curve here, this arc symbol. Right? So they might just call this, angle, let's just call this alpha or something like that. Here's where we get into the conversation of Greek letters. So let me point to this. There is going to be another handout in the either pages or in announcements in Canvas that looks like this. I photocopied this out of an old dictionary, and sadly I've lost that dictionary since then. But I love this page. Whoever designed this seemed to have a lot of insight. Maybe they were a linguist of some sort. They drew the alphabets that are the Arabic alphabet, the German alphabet, which is really just as close to English as it could get. Greek, more interestingly, Greek, Hebrew, Russian, to show you the analogy. Right? These are all derived from some mother tongue, it would seem to be. The Greek alphabet gets used a lot, right, in math and in science. So if you hear the word alpha or beta or gamma or so forth in context, right, they're referring to these symbols. And I put a highlight on the ones that get used a lot in trigonometry, right? Especially useful is pi, theta, alpha, beta, gamma, and phi. Right? Anyhow, you'll have a copy of this. Now let's discuss how we actually measure. This is some terminology now out of the way and some abbreviations. Let me do this. How angles are actually measured. I don't want to use green, it doesn't show up so well. Okay. If you have a coordinate plane, let's see if I can situate this behind here. Hopefully that is visible. Okay. Angles could be measured in reference to specific important points on the plane. This, what is normally referred to as the x-axis, is the point of 0 degrees. Right? And if you were to go this far, and you always read counterclockwise, from 0, or the x-axis, whichever you like, this point would be 90 degrees. And if you want another 90 from here to here, this would be 180 degrees. And although it might be out of the frame of the camera, to go another 90 is 270. Let me just pull this down slightly so you can see it. this point, which is the bottom of the y-axis, would be 270 degrees. And to go a full rotation would land you back in the location of 0, which is what we would say is coterminal with 360. Right? You've probably heard in regular conversation at some point somebody say, "Oh, I want a full 360." You know, you landed in the place where you started, back where you started. Let me see if I could rig this so that it is pitched a little bit better. I don't want to mess with it too much. It's not going to cooperate. Bear with me. Anyhow, it is good to recognize these. This is some information that I would memorize. Chances are that if you had maybe Algebra 2 or trigonometry in high school, right, they probably would have emphasized these 4 points at least. Right? An angle, if it is in standard position, would be read from the x-axis, the point of 0. So to say you had a ray stretching from the origin out this way, and again read counterclockwise like so, and stretched from the same origin out this way. This would be in standard position because it is running parallel to 0, and it's read counterclockwise, and the vertex is at the origin of 0, 0 technically. It would be whatever angle it is. So if it's somewhere between 0 and 90, one could estimate that it's probably maybe 60 or a little bit higher. I'm saying that just because half of 90 would probably be about there. And that's 45. So another 15 degrees, roughly 60 degrees. All right. You might be wondering, well, do I need to actually measure these angles? Not really. All right. I did actually have a photocopy of a protractor, the tool that you use to measure angles, but it's definitely not going to be important right now. All right. And if you need to, you can print it out and cut it out. Just having a cardboard protractor is just as good as having a plastic one. The only downside to it is it's not transparent. This makes it a little bit harder to read. The type that I always carry with me, a weird person, is a clear protractor. Right, mine is broken. They break too easy, the plastic ones. Okay. If you have an angle that is read counterclockwise, the way that they would signify that is if you read it this way, if it was read, well, counterclockwise is what I would say is the positive incarnation of the angle. If you would read something clockwise, I should correct myself, we would signify that by a negative. So if you read something down from the origin, or pardon me, from 0 this way, normal clockwise direction, just understand that this will be 0. This will be negative. And counterclockwise, which is more or less the way that you read normally, is positive. All right. There are names for these particular rays that make up the angle. So let me erase some of this. The side that is running along the x-axis is referred to as the initial side. 0. And the side where you actually read the angle, if this was up against a protractor, is referred to as the terminal side. Incidentally, these angles, let me pull this out for a moment. these angles, which would ride or be part of or land on each of the axes, are called quadrant angles. Or quadrantal. They're also good to know. This piece of terminology. I'm going to draw 4 of these T-shapes. A little bit nicer than that. Let's see. If you had any of these 4 situations here, where you have an angle that is riding right on 0, an angle formed by these 2 rays that would normally have a box in here is a 90-degree angle. An angle that stretches from 0 to 180. Or this type, from 0 all the way to 270 degrees. Right? These are collectively referred to as quadrantal angles. Anyhow, it's the same 4 points, right? 0, 90, 180, 270, right? And then 0 would be also 360 technically. I'm going to turn this over because unfortunately the crack that is in my acrylic plastic is a little cumbersome. Okay. Now let me see if I can put this back. It might be helpful. Okay. If you can imagine a circle drawn from the center out, a full 360. Put this in blue. I'll try to be as neat as possible. If you had a circle drawn right onto a coordinate plane, I really should take the time to make it perfect, but what I'm really after is the discussion of what an arc length is. If you have basically an angle formed in here, yes, it would be 90 degrees, right? But simultaneously, it would have some portion of a circumference, which I'm scribbling on here to emphasize. Right. Stretching from one endpoint of the ray running this way and one point of the ray running this way. And I'm going to purposely overextend it in both cases. This is referred to as an arc length. And it is strangely abbreviated by the letter S. Right. There's a formula which I'll mention again later. If you wanted to calculate this, right, an arc length, that's visible on top of the coordinate grid, an arc length, this would be a piece of terminology 5, is either a full circumference of a circle or just a portion of it. And again, it's abbreviated by the letter S. There is famously this formula, the radius times the angle that would be the angle from here to here. Right? Normally when they're talking about a 90-degree angle, which it just coincidentally is, they put a box here, right? Instead of the Greek letter alpha, the Greek letter beta, often when they're talking about an angle, they will use this Greek letter, which is referred to as theta, especially in formulas. Looks like sort of an Easter egg, or sort of a Pokeball, if you will, for a little dot there, right? Anyhow, I'm going to mention this again later. There's several formulas. This is one of them. The radius, which in theory would be from the origin here out to the edge of the circle, would be your R value. And whatever the angle from here to here, that would be the theta value. Right? If you multiply those two together, you would get the arc length. Arc lengths are abbreviated according to whatever the endpoint letters are. If there's again an A here, let's just say that there's a B here. If you see this A, B, and then specifically, sorry for the squeaking, a curve that runs like this above the two letters, understand that that's what it's referring to, an arc length. There's two types of arcs in general. You're not really responsible for this other one, but just to distinguish it. There's an arc formed by a central angle. And the central angle has the vertex at the origin. And then there's another one which is called an intercepted arc. Perhaps in high school geometry, you might have mentioned this. It's not really relevant right now. It's just exclusively this type that we're concerned with. But if it happens to come up anywhere that you say, oh, something that will look like this, an angle or an arc formed by an inscribed angle, it's going to be a little different. An inscribed angle has to distinguish it from a central angle, which has its vertex on the origin, or at the origin. An inscribed angle has a vertex on the edge of the circle. Erase this to get it out of the way, and I'll draw you a picture to emphasize. Separate these out in your mind. Here's a picture of more or less the normal situation. You have a circle again drawn onto a coordinate plane, and you have a vertex at the origin. There's rays running this way. This is the regular ordinary arc. This is the one that is relevant to us. If you have, by contrast, this situation, See if that's in frame, close enough. And you have a circle drawn onto a plane, but the vertex is somewhere out here. There's 2 rays. Notice that the vertex point would be not at the origin, which would be here, in this sloppily drawn circle, but on the edge of a circle. Right? This exists, but it is not relevant. I'm only mentioning it because if you get a problem somewhere, whether it's online, in the textbook, or in the future, right, just make sure that you distinguish these two. Right? Our formulas, specifically for Auckland, pertain to this. Right? Regular ordinary arcs rather than intercepted arc. These types of angles that have the vertex at the origin are central angles. These type of angles that have a vertex on the edge of a circle are inscribed angles, technically speaking. And, you know, these in theory have some kind of an arc length as well, but there's a different formula for that. And you don't really want to worry about it. Here's a couple of pieces of terminology to add to the increasing list, the ever-increasing, ever-enlarging list of vocabulary. Let's see. A unit circle. What is a unit circle? Well, when you have more or less this situation, when the arc length is equal to the radius, you have what is referred to as a unit circle. Oh, forgive me. Let me rephrase that. I'm getting ahead of myself, I'm sorry. Unit circle is a radius of 1. Right. 1 unit. Right. When we get into radians, all right, there's a ratio basically of the arc length and the radius. Anyhow, if you have a circle and it has a radius r and it is equal to 1 unit, whatever that unit is in theory doesn't matter. But if it is the amount of 1, all right, this is referred to as a unit circle. Last piece of terminology and then we'll move on. Sorry, I have to keep erasing just because I don't have the space. If you have this situation, nicer. where you have an angle read in more or less the normal way, clockwise, counterclockwise, like this. And simultaneously, this situation where you have, starting still from 0, but from now reading clockwise the opposite direction. What you could say about the two angles formed, the angle that you would read like this, so many degrees, and the angle read this way being some larger number of degrees. If they have the same terminal side, remember, is the side that you actually, if you had a protractor superimposed on this, would be where you actually read the number, that is the angle measurement. They have the same terminal side. You say that the angles are coterminal. All right, and some of the questions you get are find the coterminal angle. All right, there's two different situations, two different sort of formulae that you could use to calculate that. If I told you hypothetically, and remember this is starting at 0 and reading this way would be 90, and then to go all the way would be 180. If this is somewhere in between, and we'll just say 140 degrees, right? The coterminal angle, that is if you were to read from the opposite direction, clockwise as opposed to counterclockwise, would have to be in the exact same place. Right? But it would be a different number. It would basically be 220 in this instance. Negative 220. Negative because it was read the opposite way. They still are in the same location. Still have the same terminal side. Right, but just based upon having read it this way versus having read it clockwise, you end up with different numbers. Just realize they're referring to the same thing. They are coterminal angles. Okay. Now what I need to do is refer to the actual unit of measure now. Because there's basically two types. I'll give you this. It's kind of a misnomer to refer to as units, but in the case of pi radians anyway. But it's the same idea. 2 units for angles. You have, I think what people are generally more comfortable with, degrees, which have this little naught symbol written next to some number. And then there's this slightly more alien concept, which is pi radians. If it's truly pi radians, you will see that actual pi symbol. Here again is another Greek letter. Now you know pi as being 3.14, all right? But it also represents the amount of 180 degrees, coincidentally. There's going to be a conversion factor that I'll refer to in a few minutes, but anyhow, know these two types of essentially units for measurement. In the case of pi radians, there is one extra step you could go if you are asked to, which is to simply calculate radians. Anyhow, here's a little description, some fun facts about both. Degrees are basically arbitrarily decided. literally divided up. If you've ever seen, again, a protractor, I'm just going to simply pull out mine real quick here. If you have a protractor is a half of a circle. And the measurements on it are, if you were to read them, although it's very faint, 0 up to 180, right? As to be expected of half of a circle. Another full 180 would be a complete 360. But the real thing that is interesting is why 360? You know, why is it that a person, some point in history, or maybe a group of people, decided that it is exactly 360, right? And not some other number like 100, which would be more like, you know, the metric system. Don't quote me on this, but I would bet that it has something to do with the calendar. If you go back far enough in time, right, the point of recorded history is roughly somewhere between 3000 and 5000 BCE. And in modern day Iraq would be that location, Mesopotamia. Anyhow, the mathematicians at the time, you know, were responsible for or interested in calculating, events for the calendar. So I would guess that their calendar was slightly less precise than ours is right now. If you look at our calendar, it's 365 days and a quarter, right, which is very close to 360. I'm merely speculating. I don't know for a fact, right? But I would guess that they probably based degrees, right, or the concept of measuring angles on the calendar. Astrology is a less refined version of astronomy. You know, the math is not as precise. Anyhow, number of degrees total is 360. When it comes to radians, or specifically pi radians, right, it is technically unitless. Because it's not based upon a number, right, so much as it's based upon a ratio. Specifically this ratio. The ratio of the arc length to the radius. This is what I was alluding to before, somewhat mistakenly. I'll write it up here just for clarity. Arc length divided by radius, right, is the ratio upon which pi radians are based. All right, now, if you are familiar with the concept of circumference, I just need the space, so I'm going to erase this for a moment. You know that circumference is, well, pi times diameter. In upper level math, they're less inclined to use diameter and more inclined to use the equivalent in terms of radii. 2 radii are 1 diameter. So you'll see the formula written like this. Conforms a little bit more so to the good etiquette of math, where the number, the coefficient, would be up in the front. It's not wrong if you put it over here next to where R should be. 2R is 1D. But they tend to write it like this. Anyhow, if you were to arrange it, manipulate the equation so that you just have the pi on one side, divide by R here, divide by R here, you would have, in theory, a circumference divided by a radius, and that would be equal to 2 pi. Remember, a circumference can also technically be referred to as an arc length. Anyhow, the arc length, the ratio of the arc length to the radius, whatever that is divided, right, produces a pi radian, right? If it's the complete circumference, then it's exactly 2 pi. if it's a fragment, a portion of the circumference, which is usually referred to as Auckland instead, right, then it would be some fraction of pi. It's a little bit of alien hieroglyphics, right? For one thing, we're using Greek letters, not an English alphabet. And for another, it's kind of hard to sort of wean ourselves off of 360, at least if you're familiar with it. It's kind of like temperature scales. In the United States, we use the Fahrenheit scale still, right? So we have grown up associating a number like 70 degrees with it being a nice day, you know? Whereas if we used a different scale, you know, 70 degrees Celsius would be, you know, close to boiling, you know, hot water, 100 being boiling water. Let's see. Okay. If you were to go the whole 9 yards and convert to not just pi radians, but radians, right? What you're doing in that case is actually multiplying by the decimal equivalent of pi, so 3.14, whatever it is, into infinity, right? This is just numbers, right, rather than the pi symbol. As part of your measurement. So pull that down. Sorry for it being out of frame. My view of the camera, unfortunately, as it's recording, is the mirror image. So everything that I write is actually backwards from my perspective as it's recording. The end result doesn't end up that way, thankfully, but it's making it a little bit hard for me to go, oh, does this look right? Sorry for that. Anyhow, why am I mentioning this? Some questions will ask you, hey, give the answer in degrees. And other questions will say, hey, give the answer in pi radians, or go the whole 9 yards and convert it to radians. This will be basically an answer that has just numbers, just decimal numbers, if that's the way it works out. All right. Pi radians is not having to do the multiplication of 3.14. Right? You just leave the symbol behind. There is another handout that I'll have available in Canvas that looks like this. Just like this. I thought this was very cool, actually, whoever came up with this, that you can basically sort of memorize, right, these special angles, these angles that come up a lot, by using your hand. You can imagine your hand is basically making an L shape this way. That's exactly 90 degrees. And the other fingers in between 0 and 90 would be 60, 45 is halfway, and then 30. There is also 2 smaller diagrams up in the corner here, which shows you what the equivalent of different degrees are in pi radians. Like, for example, 90 is pi over 2. There are some that are good to know by heart, so I'll just draw this very quickly. As I mentioned before, it is good to know that this is 0, this is 90 degrees, this is 180 degrees, and this is 270. And if you were to go the whole complete circle, you would end up with 360, same place as 0. That's in degrees, of course. If it were in pi radians instead, this would be 0 pi, which is still 0, right? Or 2 pi, if you're referring to the 360 specifically. This is pi over 2. This is exactly pi. And this is 3 pi over 2. Right? We can calculate these equivalents using a conversion factor. Anyhow, do know these at least, because it helps when you're trying to find coterminal angles and aside. All right, let's do some calculations. This will give you more of a feel. Let me start with a model. I'm doing conversion now. This is a good model that's useful not just for math, but any science class like physics or chemistry, where you have to convert between units. Basically, be given something in degrees or inches or centimeters or what have you. And what you will do for the sake of conversion is multiply by what should be referred to as a conversion factor. If you choose the correct conversion factor and you arrange it just so, a certain thing on top, certain thing on the bottom, there'll be some kind of cancellation effect. Basically, rigging to produce a cancellation. Effect. And that will spit out exactly what you're looking for. That is, in a more concise way of speaking, what you want. You'll be given something, you choose the appropriate conversion factor, thing that relates one unit to another, and from the calculation it spits out what you want. I'll do a couple of these with you, but remember this, because I really do believe that this is practical, especially for chemistry class. The hard part is basically choosing the appropriate conversion factor and arranging it just so. The conversion factors that are relevant for our discussion right now are these two. You're either going to use pi sitting on top of 180 degrees, or you're going to use 180 degrees sitting on top of pi. Just that simple. It takes a little getting used to, of course, just leaving the pi symbol behind in a calculation. But again, if your answer has to be in pi radians, you are required to do that. In upper level math, they actually would prefer that you simply leave the pi symbol rather than convert it to a decimal, 3.14, what have you, because it will be less accurate. All right? Remember what the pi symbol actually represents. It represents the entirety of infinity, right? Rather than just a truncated portion of it, something rounded. Rounding is bad, right? Especially to a math purist. Anyhow, depending upon what you're given and what you want, you will choose either this conversion factor or this conversion factor. A conversion factor relates one unit to another. It translates one unit to another, and it would sit here in the formula or the model. Let's do a couple of these because they're cute. Short and sweet. I have to erase this, unfortunately, because I need the space. All right, suppose you had this as an example. Converting, somebody asked you, what is 15 degrees in pi radians? Again, if I were going to conform to this sort of scaffolding, this skeleton, this model that I mentioned, I'm just going to duplicate it here and then superimpose what I need to on top of it. Let's start with this. you are given something that, if you see this little naught symbol up here in superscript, 15 degrees. So you would basically position that number here, all right? And since you're going to be employing something that is a conversion factor, which itself is kind of a fraction, it's a ratio to be more accurate, put maybe a 1 under this 15. Then we're going to rig the situation so that there's a cancellation effect. All right? Remember, when things that are the same are across from each other, that is to say diagonal, as long as one similar looking thing is above the fraction lines and the other is below it, whether it's diagonally or directly one above the other, there's a natural cancellation effect. So we're dividing one thing by the other. This is true of numbers, of words, and abbreviations, the units. Just to remind you, if you had this problem, 2 sitting on top of 1 times 3 sitting on top of 2, right? There is certainly no sin in doing the brute force multiplication of 3 times 2 and getting 6, and 1 times 2 and getting 2, and then simplifying as an afterthought, right? But what you could do is spare yourself a little bit of trouble if you employ a little strategy. These 2 similar looking features are one above the line and one below it. Right? So if I rearrange them, they would really be dividing. These things essentially cancel. Right? This is again true for numbers, it's true for words, it's true for letters, and it's true for units. So when we're trying to rig our conversion factor for the same purpose of cancellation effect, we're going to choose either between this one and this one. The one that would cause a cancellation effect of degrees, all right, would be this one, because degrees is below the line here. So you would have pi over 180. Okay. And the end result will be this, right? This unit is canceled by this unit because one is above the line and one is below the line. That means that the end result, which is what we want, will be left over pi, all right? And then we would just say that it is radians as sort of an afterthought. 15 times pi is just writing these things adjacent. 15 pi. 1 times 180 is 180. There is this fraction here adjacent to pi. Remember, because this comes from the ratio of an arc length, right, which is a fragment, most of the time of a circumference, portion of it, we're going to get a fragment, a fraction, if you will, of pi, right? Whatever this fraction is reduced, right? And again, as an afterthought, we just say it's radians, because it actually is not a unit, it's a ratio, all right? Anyhow, if you simplify the fraction, it just so happens that 15 and 180, their GCF is 15, right? That may not be something that is obvious, but you could use your calculator and type 15 division and then 180, right? And it will spit out what the reduced fraction is, right? There's a button, usually on a scientific calculator, that looks like this, A, B, C. And if you type 15 and then press this button and then type 180, it'll spit out what the reduced fraction is automatically, right? There's similar features in your TI-83 or 84, right? You could enter something in the style of a fraction by going through the math button. And if it isn't at the bottom of the list that immediately shows up, I want to say you scroll over to where it says num, the num menu, and go down the list till you see n/d. If you type in what intuitively shows up as an empty space, a line, and then an empty space, and you type in 15 and 180 in here, when you press enter, it reduces the fraction for you. Anyhow, the old techniques of arithmetic are still useful. A GCF would be ideal to use because it would simplify the fraction in one step. 15 divided by itself is the GCF. They're both made of the number 15. If you do trigonometry a lot, you would know, right? It comes with experience. Anyhow, how many 15s could you squeeze into 18, right? 1 with a difference of 3. How many 15s can you squeeze into 30? 2, exactly like time. So it's 12s, right? The end result is this. Pi over 12, and again you're calling it radians. That is the equivalent of 15 degrees in this quasi-unit. Okay. All right, let me erase this. All right, let's do one going the conversion the other way. Let's say that you started with this problem, something that was in pi radians to begin with. You had pi over 6 and you wanted to convert it to so many degrees. You gotta spell out the word degrees for right now, that symbol. Maybe start again with this model. What is given to you, you're gonna write on one side, and then the conversion factor. That is the appropriate one of these two, and that will spit out what you actually want. Right. So, if this is already given to you in the style of something that's kind of a fraction, then you don't have to put a denominator of 1 under it. It's unnecessary. It's only whole numbers that you would do that for. But let's say that this is pi sitting on top of 6 times. If you're rigging this equation so that it spits out degrees, right, then you're going to have to cancel out pi. Now again, you have really only two conversion factors for our purposes. Either pi over 180 or 180 over pi. And if you're looking to cancel, think that one thing has to be below the line and one has to be above it, even if it's that they're diagonal, right, respectively. Anyhow, the appropriate choice would be this one, 180 over pi. Okay, these things, the pi symbols would cancel, right? And then you're just left with, technically it would be 180, and 6 times technically would be 1 over 6, right? And it would be degrees. Divide 180 by 6, you get 30. Pi over 6 is equal to 30 degrees. Right? Now you could cheat, and I don't want to encourage bad behavior, but do the calculations honestly, and then if you're looking to validate, right, your answer, remember there's this handout again, which shows you what these correlate to. So for example, notice that 30 degrees here is pi over 6. All right, 45 is pi over 4, 60 is pi over 3, 90 is pi over 2. These are good to sort of memorize in the long run, anyhow. Okay. Now let's say that somebody asks you to go the whole 9 yards and convert to just regular radians, never mind pi radians. Say you had a problem like this. 3 radians, and you want to convert it to so many degrees. You could do it in 2 steps, or you could kind of just build off of the model that is established already. Here's what I mean. The bottom line is that you're going to have to actually use the equivalent of 3.14, whatever it is, to and then round, because you have no choice. Your graphing calculators do in fact have a pi button, if you look at them, and it will give you a fairly accurate decimal number. Right? It's never preferred. Again, in upper level math, they tend to just use pi radians because, again, it preserves all of infinity, right? And we would like a better answer if we had to choose. You know, a rounded decimal number is not as nice as something that uses all of infinity in theory. Even if you can't see it, it's not satisfying, granted, but it is more precise, it is more accurate, I should say. Accurate. Okay. So, here's what I mean about modifying our sort of model here. If we are given something, whatever it is, whatever unit, we could adapt, we could convert it by a conversion factor right off the bat. Right. In this instance, technically, we would need a second conversion factor. This is why I say, you know, you could kind of do this as an afterthought. Just change the pi symbol to 3.14 if you feel more comfortable, or you could rig the system to produce that result, or at least take you in that direction. This will spit out what you want. In stoichiometry, the unit conversion portion of chemistry class, for example, there may be several conversion factors that you strategically rig in your equation before you do the calculation. This is to emulate that. Anyhow, if you're given 3 radians, I'm just going to abbreviate this as rad. It's rad, man. Right, and I'll stick a 1 under it to kind of imitate a fraction. And then I'll rig the system like this. The only conversion factors that I have given you are 180 over pi or pi over 180. So I'm definitely going to start with that. I'm going to include that here. Basically, the thought process is we're going to take degrees and convert it to pi radians first, and then convert pi radians into just radians, just rad. Okay. Anyhow, so if it helps, you could sort of stick this over here, or you could start in the middle. It doesn't really matter. I'm going to go with this thought process. I'm going to start with degrees, convert it to pi radians first, which means if this is what I want to end up with at this point, pi radians, then that's really what I'm going to need. Let's see, rigged like this. 180 over pi, and then for the sake of the cancellation effect, let's see, pi over 3.14, whatever it is. It's going to be this cancellation. All right. I want to end with degrees over here, so I'm going to have degrees on top, no matter what. If I want to convert from pi radians to just regular radians, the pi symbol has to be translated into 3.14. Right? Essentially what's going to happen is this. This pi symbol is going to cancel this pi symbol because one of it is above the line, one example of it is below the line. All right. Radians, I should have included this here. Would be canceled on the outer edge here because it's above the line here and below the line here. Anyhow, what you're left with is 3 times 180, which is 540 degrees. And 1 times 1 times 3.14, essentially, whatever it is, radians. Well, I canceled out the unit. Would be the denominator here. All right. If it makes more sense to you, and I certainly wouldn't blame you, all right, just convert your degrees to pi radians, more or less the normal situation at this point, and then just translate pi into 3.14 as an afterthought, right? the bottom line is that you're going to divide the number of degrees, all right, by 3.14 the decimal, and it's going to naturally shrink this number. So what you end up with is 171.8 something, the end result here. Degrees, which is about equal to, let's just say 172, if you rounded it to a whole degree. Actually divide by 3.14, whatever the decimal, however precise you want it to be, as an afterthought. Let's go back to coterminal angles. One of the questions you get asked naturally is, find, or what is the coterminal angle? Here's sort of a strategy for dealing with that. Would be basically two situations to look out for. If the angle, which I'm going to use the theta symbol to represent an angle, the angle given is greater than a full 360. All right. This would be a different strategy than, say, if you have this situation. If the theta angle given is less than 360. Basically, in this situation, you're going to subtract 360 degrees. Theta minus 360 will give you a coterminal angle. It will be, remember, 360 is one complete revolution. So you'll land in the same place as you started, right? But you'll be ideally in the range of numbers that is between 0 and 360, rather than something beyond it, like 800 or whatever. Okay. If, on the other hand, you're in this situation where you are in the normal range, or maybe something negative even, you're going to basically add 360 right, to the given angle. And that will find you, in both cases, will find you a coterminal angle. You can get, and you can keep adding 360. You could keep subtracting in this case, 360, and you could keep adding 360 in this case, and you get infinite coterminal angles if necessary. Let's see. Let's do an example of that. I need to erase this, unfortunately. Let me just put this down so you can read what I wrote here. This will find you a coterminal angle, right? Given this situation or given that situation. And if you need to do more than one coterminal angle, just keep subtracting in this case, or keep adding in this case. Here's an example of how they would phrase it. Find an angle, and a lot of times they'll abbreviate that as alpha, coterminal to 870 degrees, right? And then they might say this extra between 0 degrees and 360. When you see something written like this, sort of with these inequality symbols, really what they're just saying is that this is the normal, or in the normal range. Your angle would normally be, in this case, you're just calling it alpha to generalize, it would be something equal to 0 or bigger than it, but somehow smaller than 360. Draw a picture if it helps, right? And label it with these points, right? Remember that where you start, if it's in standard position, this is 0, this is 90, this is 180, and this is 270. If they give you something that is in radians, pi radians to begin with, maybe just convert it by a conversion factor to the regular ordinary number, regular ordinary degrees. Now, let's analyze what we have here. 870, if you had to use an inequality symbol, has what relationship to 360? Would you say that this is greater or that this is less than 360? It is definitely greater. So what you can do to figure out just the number, and I'm going to draw the picture that what it would correlate to as an afterthought. If you have this situation that your angle, and they're just calling it alpha in this case rather than theta, is definitely greater than 360, the strategy is simply to subtract. Keep subtracting by 360 until you get into the normal range. So something smaller than 360. I'm going to subtract. No, I'm going to use green. Minus 360. 0, 1, 5. 510 is still greater than 360, so I'm going to subtract again. This is in theory coterminal, but it's not in the range that they ask us for. So I'm going to subtract 360 again. 0, that's 11, that's 4. Let's see, 5, and 150 degrees. This 150 degrees is in the normal range. So where would that be in terms of a graph? If you read it as you're supposed to, counterclockwise, right, from 0, the angle that would be 150 degrees would stretch from here to roughly here. Right? Now, if this is in fact coterminal to 870, right, all that really means is that a person would keep rotating until they add up to 870 degrees. Right? You don't really have to do that, but it would prove that it is in fact coterminal. All right? I'll use in red to illustrate this point. Starting from 0, okay, that's 150, right? Then stretching past it is 180, 270, a full 360, right? If you went another complete revolution from here, all right, you would probably bypass it. Well, let's see, what's 360 plus 360? 0, 12, carry the 1, 720 would be too short actually. That's 370. Pardon me, this is 361 complete revolution. 720 would be 2 complete revolutions from 0. And then if you added another 90, which would take you this far, right, you'd have a 10, which is a little short. And then if you went another 40 degrees, no, pardon me, another 60, because it's got to be 870. 0.7870. Another 60 degrees from here would land you in this place. So one revolution, second revolution, and then up to here would be 870. The bottom line is the terminal side, which I'm highlighting in green here. It's 150 in the normal range, right? But it's 870 if you rotate several times through it. Okay. Good. All right. Let's see. Maybe do another one of these with the negative. Suppose they ask you for this situation to find an angle, and maybe just call it beta as opposed to angle alpha, that is coterminal to negative 300 degrees. Right, and they want it to be in the normal range, right? Normally between 0 and the number 360. Right? Okay. Now let's look at what we have here. If you have an angle in relation to 360, they're calling it beta in this case, as opposed to theta, and it's negative 300 degrees. What's their relationship? A negative number is automatically less than 360. So in this case, right, what we would do to calculate is add 360. Whenever you have an angle that is less than 360, and this is definitely less, as it is negative aside from the digit, to find its coterminal angle, you're going to add 360. So if we have basically negative 300 plus 360, spitefully the situation is going to subtract anyhow because of the combination of the signs. But what do you get? You get 60 degrees. Right? That means that negative 300 should be in the same place as positive 60. Let's draw a picture to make sure. Right. If this is normally 0, 90, 180, and 270, and this is also 360, it's the same location. Negative 300 is something that you would measure clockwise. We think of clockwise as the appropriate way to read time, but remember when you're reading angles, it's actually backwards. All right, we'll start at 0, and then we would go 300 this way, in this direction, clockwise direction. That would be 90 going just that far. Right? This would be 180, this would be 270. 300, negative 300, would have to be somewhere in here if you read it clockwise. That's negative 300 degrees. Right. Anyhow, if this is 270, you know, if you were to sort of reverse the situation, this you would see is 300 that way. All right. To go the whole 9 yards back to the line of 0 or back to 360, what's the difference? Would have to be 60 degrees in here. Okay. They're coterminal, right? 60 read from this direction is coterminal to negative 300 read from this direction. They land in the same place. That is all the coterminal really is referring to. Now the last thing is some formulas and a description of what they do. One of these already mentioned before. Here's what we would need. arc length, and as I mentioned, it's strangely abbreviated as S. Right? Arc length is a distance, basically, along the edge of a circle. Ideally, it would be the whole full distance, which would be 360 degrees. It would be a full circumference, but an arc length could be something smaller than a full circumference. Anyhow, it's S is equal to R times theta. So what you will have to do is plug in whatever the radius is, whatever number is that is quoted to you that is a radius, and whatever the angle. And this would be, in theory, a central angle. Sorry, this is sloppy. Technically, it has to be a central angle. It just means that the vertex is at the center, at the origin. Right. They might ask you to give the answer in degrees. Let's see. And then you convert it to radians. And then in theory, you convert that to pi radians. Right, so here's an example really quickly. Times arc length given a radius of 10 units, whatever the units are. And then they'll use this phrase, subtended. Don't be intimidated by that. By an angle of 215 degrees. Right. Answer in radians. A couple of points to clarify. We're going to definitely use this formula if they're asking us to find S, because that's what the abbreviation is for arc length. If somebody says to you this phrase, subtended, all right, it means created by two rays, stretching out from the origin. Two rays that intersect. This is getting sloppy. I'll write it down here. Created by two rays intersecting the edge of the circle. That is all that subtended really means. Right? So for example, if you had a circle and two rays, a ray, let's just say ideally running this way from the origin, and then the second ray, as you know, the two rays together form an angle. This would be the angle subtended. You could say it is the arc length. Same difference, really. An arc length subtended by the angle here. Okay. Anyhow, you're going to plug in the values given. So, although this is sloppily written, you have to use the number 10, and you have to use the number 215 degrees. Right? They also want the answer in radians, so we'll have some conversion as an afterthought. For the lack of real estate here, I'm going to erase some stuff, but I'm going to plug those numbers into the formula. 10 would sit in here. 215 degrees would sit in here. 10 times 215 is 2,150. Right, degrees. Right. Now, first of all, we'll convert this, which is an amount of degrees, to pi radians, and then we'll just convert that to regular radians, which is to basically, you know, employ 3.14, whatever it is. So, if we have, again, if we're given this, and we're going to convert it via a conversion factor, right, this will spit out what we want, and then as an afterthought, we'll incorporate 3.14. If I have 2,150 degrees, right, and I want degrees to cancel, then of my two conversion factor choices, which go here, right, I'll put degrees on the bottom, and it will be 180, and the pi symbol above the line. And I'm just going to write the word radians here because maybe it makes it more obvious what the end result will be. And, you know, this cancels this, and you can treat this as if it was a fraction by sticking a 1 under it. 2150 will have a pi attached to it, radians, and below it will be 1 times 180, will be 180, and then we'll pull some tricks here. Okay, you could simplify the fraction using a calculator naturally if you want. We could pull a mental math skill, which is that if you see pairs of zeros, it would be equivalent to dividing 215 by 18 instead. Okay, I need the space, so I'm going to erase this up here. Save that. We have this calculation. We have 215 pi over 18. And this is, they just want it to be in regular radians. So as an afterthought, what you can do is use the equivalent of pi, which is 3.14 multiplied by this fraction. All right, using your calculator and the pi button that is actually on a TI-83 or 84, you get a more precise answer. And you end up with something like this. It's approximately 37.525 radians. You know, if you want to round it, you could say, if you round it to a whole number, about 38 radians. Okay. Just incorporate 3.14 in place of pi as an afterthought. Okay. All right. Let me mention some more formulas and then I'll let you go. Let's see. Where's this? So we have, just to reiterate, arc length, which is S is equal to R times theta. And then we have this as well, which is also interesting. The area of a sector area, A is an area, is equal to 1/2 theta, the angle, times radius squared. There we a second. What is the area of a sector specifically? A sector is a wedge, right? For all intents and purposes. You know, if you had a pizza, it would be circular. And when you eat a pizza, it's chopped up into slices. When you think sector, right, think of a wedge, or maybe appropriately, a pizza slice. Right? It's not going to be the entire thing, unless you're a real greed ball, all right, who eats the entire pizza themselves. All right. Sorry. But anyhow, you could calculate the area of one individual slice, one individual wedge, one individual sector, if you use this formula. Okay? They may specify in a problem that they want the answer to be in pi radians or regular radians. I would convert to that as an afterthought. Just plug the numbers in that are given to you up front, and unless they demand that you do it some other way, and then convert as an afterthought. Okay. And there are these two concepts. There's linear speed. And then you'll see if I can fit this in the frame, and I'll have to move it. Something called angular speed. Put that up here. Two distinct formulas. The formula for linear speed is this. V is equal to the arc length over t. And an arc length is S, and t is equal to time. All right. Now, just for the sake of analogy, I'll put this in here. You've probably heard of speed in general, so I'm going to put a little thought cloud just above this for the sake of analogy. What is speed normally? Speed normally is a distance traveled in an amount of time. We have essentially the same concepts here, except that it's an arc length, right? And time is down here still. Sorry, that's not a frame here. We're just calling distance an arc length instead, right? And we're calling time still time. Okay? When you think linear speed, just like when you think of area of a sector as basically being about a pizza slice, right? Think a circumference, or some portion of a circumference, unraveled. What happens when you take something that is circular, unravel it, it's linear, right? When you see those, occasionally as you're traveling, you see somebody painting lines on the street, like the white dashed line or the solid yellow lines on the street. They have a roller, literally, that has paint on it, and it's unraveling, and it's making a mark on the street. Right? That's essentially a linear speed. Right. This is along a straight path. It's translating something circular into something linear, straight. Okay. And it's adapted from just the concept of speed is equal to distance divided by time. When you have an angular speed, we use this symbol. It's not a W. This is omega. It's another one of those Greek letters. It's a lowercase omega specifically. Omega is equal to theta over time. This is basically rotations per unit of time. When people had records, and I suppose they're making a comeback with records, right? They used to have rotations per minute. 33 RPM is 33 full rotations of the record in 1 minute. A 45, which is a smaller record, right? It's 45, it's a little bit faster. It's 45 rotations per minute. Now, in theory, if you go back far enough in time, like my grandfather's generation, they had 78s, and they were somewhere between the size of a 45, which is small, and a 33, which is, you know, full-size record. A 78 would be 78 rotations per minute. And were made out of, I think, a different substance too. They were more brittle, I believe. Anyhow, rotations per minute is more or less the normal situation, but it really should be per unit of time in general, right? In this case, the speed equals distance over time formula is adapted to not be an arc length, but an angle instead. An angle given. Okay, so probably degrees. And if not, you can translate it into radians or pi radians. Okay. Let me leave you two sort of adapted formulae. I don't think this is going to come up in any of the homework that you see in my open math, but just in case. And if you take a physics class, it might be handy. What happens in physics a lot is that you have basic formulas that are then adapted to sort of combine with one another. You'll see that now. Right. If we're saying that angular speed, omega, is equal to theta, an angle divided by time, and in the same breath, we're saying that arc length is equal to a radius times an angle theta. And you could combine these, and you would get this as a formula. Basically rearranged, you could insert ST in here. Or you could rearrange this and insert this in here. A more practical version for us would probably be this. Taking this and inserting time times omega in place of theta. So you'll see this. Arc length is equal to radius times omega times time. It isn't wrong to do it the other way, but this will be handy, more handy perhaps, for the relative and problems I had for the textbook when I originally designed this, textbook problems. Let's see. Okay, save that. Here's another one. And if we have this established, if we have linear speed is arc length over time, and now we have this adapted version of those other two formulas combined as r times omega times t, radius times the angular speed times time. If we insert one in the other, that is, if I take what s is equal to and insert it in place of the arc length, then we have this adapted formula. We have r dot omega dot t over t, which simplifies to this. The angular speed can be calculated the linear speed can be calculated from the angular speed if you know the radius as well. Right, so now this one, if it comes up, and I don't think it necessarily will because I'm not using the textbook problems at this point. But keep this on hand. If you take a physics class, right, you'll end up with situations where you have to combine formulae. Formulas. Okay. All right. And we're at the hour 50 mark, so let me stop. I'll give you some reminders here. All right, for homework, and it's just to try, just for the experience. In the future, I mean, I would tell you ahead of time, all right, this particular homework, I'm going to record it, all right? I would still encourage you, if you can, if you have access. I know that it may be tricky under the circumstances that we're living. But for the sake of experience, all right, try this. For homework, do section 7.1 practice. In my open math.com. Okay. Virtually any homework that you get at this point would be one of those things. It's the only thing that we could do remotely. And like I said, I will give you some photocopies, well, the virtual photocopies of relevant diagrams and stuff in Canvas. Right. I'll try to, when I upload the video, and actually post a link in announcements, and I'll see if I can get just the relevant diagrams in the same announcements. You don't have to go digging for it. Anyhow, just merely for the love of learning, all right, and for the sake of experience. All right. For right now, try this section. All right. And again, if I need to get some more grades, I don't know. Depends. In the future, I would tell you ahead of time. I would say, all right, specifically section 8.2 or whatever, I'm going to record. Right? And you'd have time to work on it. I can't give you a test at this point. It is just not possible. I can't collect it. I can't proctor it. Your grades in Canvas are current, right? And no one is failing this class, all right? It's just not going to happen, all right? The worst case scenario is you get a D. All right, just based upon what we have at this point. If the semester ended tomorrow, I have grades for you. I'm gonna try, all right, to periodically update. I was on the quiz that I had planned for my open math anyhow. That's coming in the future, and I'll tell you ahead of time. Okay, stay safe, folks. All right. Thank you for listening.